Well, let's go ahead and take a look at this second Stop 80 or an NMI hardware failure bug check. All right, let's go ahead and fire up the debugger. We'll put it in administrative mode and open up the crash dump. We'll go ahead and select the second demo here and bring it into the debugger. So here we note right away that it's a Stop 80 or an NMI hardware failure. In this case, just like the last one, we forced a crash because the server hung. We can go up to the top and see that this is a 8.1 kernel or version 9600, which is Windows Server 2012 R2. In this case, we have 16 processors and it's the x64 architecture. So go ahead and start out on our analysis. It says that it was probably caused by Intel ppm.sys, which is actually the idle loop. The Intel power management driver gets involved there, that if the system is truly idle, it will actually park the CPU. Chances are that it was caused by this Intel ppm.sys driver is very unlikely. We'll go ahead and start off with the bang analyze-v-hang command. See if that turns up anything. Again, it was trying to scan on blocked locks. We'll go ahead and page back up and take a look at that. Here's the start of the command, bang analyze-v-hang, and it said that it was trying to scan for threads blocked on locks, but it couldn't get this e-resource type. So again, not too much help there. As we scroll down, we can see the stack of the current thread at the time. Yes, indeed, it was running in the idle loop, and there's that Intel power management driver I was talking about before we got interrupted and ultimately the system bug checked because we forced a crash dump. So where to from here? Let's go ahead and take a look at that current thread that was running at the time. Here we are, it's just the idle thread, and we look at the stack. Yes, that's the stack we just saw. It's in the idle loop before we bug checked the system. So nothing much was happening with the current thread. Another thing we might want to try is bang locks to see if there were any locks outstanding at the time. So this goes through the crash dump and it quickly tries to determine if there are in fact any locks out there that are being held and potentially causing the system to hang. But as you can see, it says there are 146,000 locks, but none of them are held at this particular time, so it's not a locking issue. We can do a few other commands like bang vm1 to see if we have plenty of memory, because we're just sort of fishing around seeing why this server may have hung. All right, we'll scroll back and take a look at the physical memory utilization. Here we've got the bang vm1 command, shows me my page file. It does have quite a bit of free space in the page file, so not sure that it is a memory issue. Here the available pages of memory shows that we have at least 8 gig free, so it really doesn't seem to be a shortage of memory. So let's keep on looking around. I'm going to go ahead and do my favorite bang running-it command to see what was running on the different CPUs. So let's go ahead and scroll back here and take a look at that. Here's the bang running command that I issued. On CPU 0, we see that it was executing in the idle loop. CPU 1 was also executing in the idle loop. Same thing with CPU 2, CPU 3, 4, 5, 6, 7. Now CPU 8 was executing in the idle loop before we forced a crash on the system. CPU 9 is in the idle loop. So is 10, 11, 12, 13. All of the CPUs are idle. So let's think about what we got now. We've got an idle current thread. All the CPUs have got idle threads running. We have plenty of memory. We have no locks. So it's not too clear what may have caused the system to hang at this point. So we're going to cast a bigger net and do a command like bang stacks. This will show me all the threads on the system that are running and what function they're running. So as you can see, at first it shows us all those running threads doing the idle loop, and then it starts telling us what else is out there. And you can see that the threads are mostly all blocked, this middle column here where it says blocked. This is because on a system that may have many different threads, 99% of them will always be blocked. They're waiting for some sort of input, whether it be from the keyboard or an I/O coming back or an event ready to be set. It's not uncommon to see many processes or threads that are blocked. But what is uncommon is what we're seeing now. Look at this. Many of the threads appear to be the same one. This NT bang FNODOBFM, then a string, and then some offset of 55 to Charlie 7. And we see this again and again and again. It looks like there's some sort of problem. All these threads that are executing the same thing. Well, let's take a closer look. I'm going to issue a control break command. Control break is how you stop a command from executing if it appears to be taking a very long time. So remember that. Control break will get you out of the current command. Now, here's a little trick that you can actually do is .log open, then perhaps give it the location of a file. So I want to send all the output that's typically going to the screen to an output file so that we can maybe massage the data a little bit. So I'm going to do the .log open command, and then I'm going to do, say, a bang stacks command. And it's going to send it to the output to the screen and to the file. And it's going to take a long time. So I'm just going to interrupt this one right here, and then you would ultimately do a .log close to close the file. So that is effectively how you capture any output that's going to the screen. So at this point we'll go ahead and bring up a command prompt where we can take a look at our stacks.txt file. And what I'm going to do is just pull out those threads that were the $FNODOBFM to see how many of those threads there are. So I'm going to do a command like find string, looking for that FNODOBFM string in our stacks.txt file, and send the output to maybe FNODOBFM.txt. And so that command runs. Then we can use something like Notepad++ to take a look at that FNODOBFM.txt. And here we go. We'll just jump to the bottom because it just pulled out only those records. And you can see that there were 16,383 of these threads. That's one number short than 16,384, which, as you may know, is an even power of 2. You have 1024, 2048, 4096, 8192, and finally 16,384. So we have hit a ceiling. We have hit the maximum number of system threads that you can produce. So this appears to be what's known as a thread leak, where we've got literally over 16,000 threads that are causing the system to hang. What we can do is take a look at some of those threads to see if we see anything interesting. So let's go ahead and go back to the debugger. We can take a look at some of these threads, for example this one right here, and we'll do a bang thread command on that. And we'll take a look and see what it was executing over here on the far right. You can see that it was a system thread, a worker thread, that was executing in the MS iSCSI driver, trying to do some sort of SP wait and remove connection. So turns out if we looked at all of those different threads, they were doing the exact same thing. So we can take a look at the actual code that was running by taking the MSI SCSI plus the offset and using the UB command to unassemble there. This is where the call is off to that. It's removing a lock and waiting. Not sure why, but we now know essentially what the problem is. We've got a thread leak, and it's associated with this MSI SCSI driver. So we would want more information from this MSI SCSI driver to give us perhaps its date. You can see it's March 10th, 2017, or you can do the lmvm command on the same MSI SCSI driver. It gives you a little bit different type of information. But the fact of the matter is, this driver was produced on March 10th, 2017. Well, as it turns out, to make a long story short, there is a known issue. If you just search Bing or Google with things like a thread leak in the MSI SCSI driver, lo and behold, look what we see here. That this particular hotfix will address an issue with a port and a thread leak causing unresponsive systems due to iSCSI target connection failures. So Microsoft introduced this buggy MSI SCSI driver in the March timeframe and released it in several security hotfix, and it was ultimately fixed in the August monthly rollup. This is the July 18th preview of the August monthly rollup. So that's our goal here, is to look at the crash and then intelligently search the internet for potential fixes. So in summary, the server hung because of a bug in the MSI SCSI driver, which caused a system thread leak. Installing the appropriate update rollup fixed the issue.